Hi everyone, this is your notes video for dilations and a little bit about similarity and similar figures. So for this one, I put most of the notes together for you and I just have some practice problems for you. So you won't see any slides on this video. I'm going to walk you through your student note page for dilations and similarity. So let's jump into it a little bit. Okay, so a dilation is the only type of transformation that we have not talked about yet, right? Because it is not a rigid motion. If you recall, a rigid motion is something, it's a transformation that will not change the size or the shape of the figure. Okay. A dilation, right, is a transformation that changes the size of the figure, but not its shape. Okay, so we're going to change size, changing size, but not shape. Okay, and we're changing it by something called the scale factor, right? Which we represent with this variable k. Right? So essentially what you're doing is you're taking a shape and you're making it bigger or smaller. You're enlarging it, making it bigger, or reducing it and making it smaller. Okay. It's a lot like what you do when you're changing the size of photos or images on a Google slide or a Google Doc, um, things like that, right? Same shape, different size, right? Okay, so scale factor, the actual definition of scale factor is how much a figure changes in size. Okay, so it gives us a value for how much bigger or smaller a figure becomes, right? Maybe it becomes twice as big, or 3.5 times as big, or a third as small, or something like that. Okay, the actual number will tell us if the dilation is a reduction or an enlargement. Okay, so an enlargement happens when k is greater than 1. So when the scale factor is greater than 1, that would be like twice as big or 1.5 times as big, etc. Okay, a reduction is if the value of k, the scale factor, is between 0 and 1. Okay, that's saying I'm going to make this a quarter as large or half as large as it was, right? So typically you're looking for a fraction or a decimal, but a proper fraction, not an improper fraction. It just has to be a number between 0 and 1. Okay, if you have a value of k is exactly 1, k equals 1, that is a rigid motion. Okay, a value of k equals 1 basically just means that I'm taking the shape and I'm multiplying it by 1. I'm multiplying its size by 1. So that means that the size is not going to change. Okay, just like rotations, dilations also have a center. Okay, so typically, right, you'll take your shape and you will have it shrink or grow around a fixed point. Okay, for our problems, most of the time that point is going to be the origin, because that's the one that we know functions about, and we can more easily solve those types of problems, right? And actually figure out where coordinate points end up and how long sides are and things like that. Okay, so if you think back to when we were talking about function notation for translations and reflections and rotations, right? We had these functions where we have the original coordinate and then an arrow and then the function or what's happening to each coordinate on the right hand side. So for dilations, what you are doing, which I'm hoping you kind of have picked up just from how I've been talking about dilations, is that you're taking everything and you're multiplying the x and y coordinates, the side lengths, whatever it is, by the scale factor, right? So you're taking each of your values and multiplying it by x. That's what this function says right here. Okay, taking my original coordinate points and multiplying them by k. All right. Below that, you're going to see here's a couple of images of what dilations might look like depending on where the center of dilation is. So this is just to give you an idea of how these things grow and what it looks like when they do. So I'm hoping that you can see on each of these, there's the center of dilation is point O, and then you can notice going out from it, there's these dashed arrows. Okay, those are called directed line segments, right? It's basically showing you how each point moves and how it changes as as the figure grows or shrinks, right? So the larger, for example, if I'm making my original triangle here in the middle larger, right? The bigger the scale factor is, the further out all of these points, point B, point A, and point C, the further out they will go from along this line here, right? And then they'll also like shrink along this line as well. Okay, it's kind of just giving you a direction and showing you how the figure is changing. Okay, right. Like I said, most of the time, our center of dilation will be the origin. So sometimes you will see if the origin, for example, is inside the shape, like you can see here on the left, then the shape is going to kind of grow and shrink around the origin. But if the center of dilation is outside of the shapes, which you'll also see, it will kind of grow from that point. It will grow from that point out in the same direction that the directed line segment shows you there. Okay. All right. Then last thing for like notation and things, if you remember the function notation, right? That was kind of the first thing we learned, and then I also told you a little bit about vector notation. So dilations also have a vector notation. Remember, it's kind of like the shorthand, so that way you don't have to write the whole function out. You can just write the vector notation, and it's shorter. It's less for you to write, but it provides you with the same information. So the vector notation for dilations is a capital D. Right, that's how we know we're dealing with the dilation. The first thing that you'll see on here, right, the first input is the center of dilation, okay, which for us almost all the time is the origin. Okay, and then what comes after that, the number that comes after that is the scale factor. Okay. All right. So the next part of this is similarity, right? So we have been talking previously about rigid motions and transformations that make shapes that are the same size and the same shape. So they make congruent shapes. So dilations, if we go back to the actual definition of a dilation, it will change the size, but not the shape of a figure. Okay, so dilations are an example of something called a similarity transformation. Okay, the figures are similar, meaning they have the same shape, okay, but they're different sizes, right? That's what similar figures are. Okay, so you have this definition here. The pre-image, which is the original picture, and the image have the same shape, but different sizes. So dilations are really our only type of similarity transformation. Okay, and then you also have a definition of similar on here. So just keep in mind, right? Remember, similar means same shape. Similar means same shape. Okay. All right, then the last little thing before I do some examples is we can do compositions of transformations with dilations as well. So we've done these previously just with translations and reflections and rotations. Remember, a composition of transformations is just when you do more than one transformation in a row on the same shape, right? So again, we're using our vector notation and we're still following the same rules, that we're still going to read the composition from right to left, right? Or from the inside out, right? So you always do the one on the right first, right? So see, in this example, we start with this dilation and then we do the rotation. right? And I kind of give you an example here and show you how this coordinate point would change. So we're taking the original coordinate point, 1, -3, and then multiplying it by a scale factor of -2. Okay, so that point is going to grow and also kind of go in the opposite direction. So we end up with 1 times -2 is -2, -3 times -2 is +6. Okay, and then it says, then after that, perform the rotation with the new coordinate. So I took this new coordinate and I'm applying the rotation, the 90-degree counterclockwise rotation rules to this new coordinate, so not the original one. So that rule is you switch the x and the y and you change the sign of your new second value. So -2, 6 becomes +6, +2. All right, so give me a second to reset my screen and I'm going to do a couple of examples for you in this video as well. So I'll see you in just a moment. All right, y'all. So here we go. Here's a couple of examples dealing with dilations and scale factor. Okay, I've filled in most of this example for you, but I do want to talk you through it a little bit, and then we'll also write the function notation um, and the vector notation for this as well. Okay, so we have triangle DEF, right, which is the smaller triangle here. Notice that the smaller one does not have the little dashes on it. Okay, this is very, very important to keep in mind. Okay, we have to know which is which, right? And the reason for that is because if we want to calculate a scale factor, oops, if we want to calculate a scale factor, it's always the new coordinate point divided by the original coordinate point, right? I'm saying coordinate point, but it could also be a side length or anything like that, right? Because the way that we wrote these functions, remember, is that the new point was k, the scale factor, times the old point, right? That's what we saw in the function notation right here, right? Because this right here is the new point. So the new x equals k times the old x. Okay, so if you want to figure out what the actual scale factor is, right? If you knew, say, the new coordinate point was 5 and the old coordinate point was 2.5, right? Then you would divide those in order to figure out what the scale factor was. Okay, so here, right, it's very important to pay attention, right? Because if you don't know which is the original and which is the new shape, then you'll get your scale factor incorrect because you'll be going in the opposite direction. Okay, so here the smaller triangle is the original. So we're going to dilate this with the center at the origin, okay, and a scale with a scale factor of 2. Okay, so what's actually happening here, right, is we essentially are taking this coordinate point, the origin, right, and drawing ourselves a directed line segment. This is just a way for you to visualize what's happening and like what direction the points are moving, right? So it's almost like, I don't know if you all ever played with those um, plastic things that you could pull and make bigger and smaller, and it would kind of like either become bigger or collapse in on itself, right? The directed line segments here just kind of showing you the motion of what's happening, right, as the figure gets bigger or as it shrinks. Okay, so most of the time you're not going to be asked like what are the directed line segments or to draw them. It's just to help you kind of visualize what's going on. Okay, so here I want to take my original shape and dilate it with a scale factor of 2, right? So all I'm doing is I'm taking all of my coordinate points and multiplying everything times 2, right? So -2 times 2 is -4. 3 times 2 is 6, right? So point D goes from -2, 3 to -4, 6, which you can see here, right? If you look at the actual picture, right? The point D is negative 2, 3, and then the new point is negative 4, 6. Okay, and then we do that to all three of our coordinate points so that way you're multiplying everything by the same number, right? That will guarantee that you keep the same shape, but obviously you're just dealing with a different size. So if I wanted to write this in function notation, I would write x comma y becomes kx, so 2x comma 2y. Okay, so that's my function notation. If I wanted to write it in vector notation, it would be a dilation around the origin, so a capital O, comma, with a scale factor of 2. Okay? It really is just multiplication, y'all. So don't make dilations and scale factor like this super frightening, scary thing. It's just multiplication. Okay, so here's another example for you, but with a smaller scale factor. So as you can see, the bigger shape here is the original, right? See, no prime notation, no dashes, right? But I'm still dilating around the origin. I know it didn't say here that you're dilating around the origin, but if it doesn't say it, you can just assume that it's the origin, right? So here you could draw your directed line segments, but you would kind of see how these points all kind of essentially like grow out of the origin, right? It's almost like the origin or the center of dilation is literally like the center of like a flower or something, and the actual shape is growing or expanding out from that point. Okay, so since this is a scale factor of 1/2, right, this is a reduction. Right, I'm going to make this shape smaller, which you can kind of see in the image, right? So I have my original coordinate points, right? And I multiplied by 1/2. So I did times 1/2. Remember that multiplying by 1/2 is the same as dividing by 2. Same thing, okay? So I took all of my coordinate points and cut them in half in order to get my new coordinate points. So my function here would be x comma y becomes, and then it's still kx comma ky. And k in this case is 1/2. So it would be 1/2 x comma 1/2 y. Right? And if I wanted to write that in vector notation, that would be a dilation still around the origin, but my scale factor this time is 1/2. Okay? All right. So this is a slightly different type of problem because what it's asking me to do is determine the scale factor. Okay, so remember, right, in general, with the function notation, what you're doing is you're saying the new coordinate point equals the scale factor times the old one or the original. Okay, that's what the function notation tells us. So we can work backwards from the coordinate points that we have in order to figure out what the scale factor is. So it'll be the same no matter which coordinate point you choose. So I'm going to go ahead and choose the k's right here and kind of work with those. Okay, so my original point, the original point k is 1, 2, 3, -4, +2. So -4, +2. So this is my original. All right, my original coordinate point, or you could say my old coordinate point. Okay, and then k prime, that's my new point, right, because it has the prime notation, is -6, +3. So this is my new one. So what I'm going to do is I'm just going to pick one of these. You can pick either the x's to write a formula with or the y's, but you don't have to do both. You can pick one and then use the other to check to see if your answer was correct. So remember my formula here is that the new coordinate point is equal to k, the new value equals k times the old value, right? Another way that you can write that to get k by itself is to say k is equal to the new value divided by the old value, okay? So I'm going to use the x's here, right, and plug them into my equation. So my new value is -6 equals k is what I don't know. Remember, k is the scale factor here, the lowercase k. It's different from the coordinate point, which is an uppercase k, times the old value, which is -4. Okay, if I wanted to solve this, right, for k, I would divide by -4 on both sides. So see how you end up with when you take this original equation and you manipulate it and solve it for k, that you get new divided by old? That's exactly what's happening right here. Right here, because this cancels out, this is new in black up here at the top divided by old, green, okay? So that tells us that k is equal to 3/2. Right? Which is, if you want to do that as a decimal, that's 1.5. Okay, so that is my scale factor. And I could check to see if it works with the y coordinates, and it does. Right? If the scale factor is 1.5, 2 times 1.5 is 3, which is exactly what it's supposed to be. All right. So give me a sec to clear my screen off. I've got I think 2 more examples for you that deal with the composition of transformations that have some dilations in there. All right, y'all, last 2 examples here. So this first one I already have worked out for you, and then you may want to try the second one on your own. So this is a composition of transformations. I'm starting with an original triangle, ABC, which is this triangle that you see right here. Okay, it says to perform this transformation, this composition of transformations. So notice I'm always going to read this way from right to left. So I'm going to do this reflection over the y-axis first and then do the dilation. So those are my steps right here. Okay, and I wrote the function out for you so that way you could see how the points changed. Okay, so I took my original and I flipped it over the y-axis. So what that did is it made all of my x values negative. So 1, 2 became -1, 2, 5, 2 became -5, 2, etc. Okay, so that's step 1, right? So I did the reflection, check that off, and now I have to do the dilation. The dilation is around the origin with a scale factor of 2. So my function is xy becomes 2x, 2y, right? So remember, 2 is your scale factor, your k right there. That's what you're multiplying by. So I'm taking my points here that I got after the reflection, right, and multiplying all of those points by 2. Because that will ensure that I'm following and doing this in the right order. So all I did here is I took these coordinate points and I multiplied every coordinate point by 2, right? And so you get this much larger figure here, which you can kind of see. You can kind of connect the points that have the same letter. See that? These are your directed line segments, not drawn very well by me, but you can see how the lines connect and how the shape kind of grows out of the origin there. Okay, so for this one, I have your original triangle right here. And this is the composition of transformations here, right? So I want you to see if you can do this one on your own. I wrote the functions out for you so that it would be a little easier for you to complete and do the coordinate points. So try to figure out what the new coordinate points would be for each step and then draw it on here. Okay. All right. So I'll see you back in just a second to check your answer. Whoops, hold on, y'all. Before you do that, sorry. I realized that I forgot to put what these actual coordinate points were, like which one was point A, which was point B, which was point C. So this one here is point A, this is point B, and this is point C. Sorry about that. Okay, now give it a try and see what happens. Sorry, folks, one more thing. I realized that my function here was incorrect. I had a typo in there. My because my scale factor here um, is 1.5, not 2.5. Sorry about that. Um, so multiply all of your values, all of your original coordinate points by 1.5, not 2.5. And then this is a rotation, not a reflection. Okay. So I kind of have it started here for you. There's your original coordinate points. I filled them in for you. So take those original coordinate points now and follow the function and see what happens. Okay, so sorry, I think I caught everything now. Give it a try and then check back with me to see how you did. All right, folks, so here is your completed composition of transformations. So I took my original coordinate points and dilated them first. So I multiplied by 1.5, right? I multiplied all of my values by 1.5, and I got that new triangle that you see in green, so a little bit bigger than the original, but same shape. And then the blue triangle represents the counterclockwise rotation, right? So I took all of my coordinate points from the green triangle, switched the x and y, and changed the sign of the new x coordinate, the new first value, right? And then you end up with that lovely blue triangle right there. Okay. All right. So that is it for this notes and examples video on dilations. I've got one more for you on dilations that just has some extra practice problems. So I'll see you guys in the next video. Bye, everybody.